Welcome to the lecture series in computer science. As a part of this series, we are in artificial intelligence course, and in this course we are in unit 3, and in this module it is a continuation of the last module where we saw the logic, and in this module we would be seeing some examples of forward chaining, backward chaining and resolution. The forward chaining and backward chaining, I will take a few examples from proposition logic, and resolution we will include both proposition as well as predicate logic. First, let us see the forward chaining from proposition logic. Consider three basic statements like A implies B and B implies C. I have just given it as normally A as the first one while I am speaking. Here use forward chaining to determine C and whether it can be inferred. So, taking A and then A implies B, using the rule of modus ponens, I would get B, and with this B I take the second rule with B implies C, this is the axiom, and then I get therefore C. So, if we see, we are going from the axiom, these are called as the axioms, and from the axioms, from these facts we are able to get back to C, to the conclusion which is C. So, we are going in the forward direction, therefore, through forward chaining we can infer C. So, this is the first example. In the second example, in a similar way. So, here in the last example we have seen with formulas. Now, we will see a real world example or a practical example. Let us say we are building an expert system for diagnosing flu, and assume in the knowledge base we have these facts, where the first fact is if there is cough, there is throat irritation, and if there is throat irritation, there is fever, and if there is fever, then it is true. And another observation that we have is cough is true, which is an observed symptom. Now, can we infer the patient has flu again using the forward chaining, and within the logic we will be using again the same rule of modus ponens. So, how do we do that? Let us go with the first one, which is I will just name the rules as 1, 2, 3, 4, so that we are able to get properly using those numbers. Now, the first one would be cough implies throat irritation. If there is cough, then there is throat irritation, and cough is true. Suppose we take this 4, cough is true, and then the first one cough with throat irritation. I am just naming it as T I just for the shortening the entire thing. So, therefore, I would get the throat irritation is, again this rule we are going to use it as modus ponens. Now, with throat irritation we have another rule here which says T I implies fever, which is from second rule. Again, while using modus ponens we get fever, and which is again the conclusion. And fever, this implies fever implies flu, which is again the rule 3. So, therefore, this flu we get as a conclusion. So, this is how a forward chaining helps to move from the set of axioms or the facts to the conclusion. So, this will be the similar case can be extended to predicate logic also. Now, coming to the next example of the backward chaining. So, backward chaining otherwise is called as goal oriented reasoning, where we would move from goal to the axioms. So, we will check whether the goal is there, and then from the goal we are going to check any of the facts within the knowledge base. So, if we see in this example, there are 4 facts: A implies B, B implies C, C implies D and A. And the question is, using backward chaining, can we determine D? Is D or is D entailed? So, if we check, take D, we want actually D, and to get D we want C, and to have C we want B, and to have B we want A, and this A is already, this exists in knowledge base. Therefore, D is entailed. We can say that D is entailed. So, in backward chaining, we move from the goal and see whether that particular fact backward, by tracing backward, is available within this knowledge base. Now, this is a scenario, practical scenario. Assume this is an home automation case, where we are going to see through backward chaining. Okay. So, the scenario is, assume you want to turn on the alarm based on certain conditions. The goal is, should the alarm be switched on? So, the knowledge base consists of 4 facts. Again, I will just name it as 1, 2, 3 and 4. Assume that motion detected. If there is motion detected, then there is a possible case of intrusion. If there is a glass break, then there is a possible case of intrusion. Glass break is window glass getting break, someone sneaks in, then there is a possible intrusion. And if there is possible intrusion, the alarm should be on, and we have also observed that the motion detected is true. So, from these 4 facts, can we say that the alarm should be switched on? So, how do we do that? We will go backward. So, if alarm is switched on, so if alarm is on, that is dependent on possible intrusion from 3, and possible intrusion here there are 2 ways. One is through motion detected and another is through glass break. This is actually an OR condition. So, if we are going to take through motion detected, and this is via 1, and then motion detected is actually true according to 4. Motion detected is true, which implies it is present inside this knowledge base. So, since it is present in this knowledge base, this alarm should be switched on. So, the conclusion is alarm should be on, This is the conclusion. So, this is how the backward chaining works. Now, we will get on into another automated one of resolution, where we can reason out using inconsistency. So, this acts as an inconsistency. The reason is, we are going to check within this knowledge base all these clauses whether it will lead to a null clause. So, if we see the first one, not A or B, and if we take the third one, A, not A and not A will go away. So, we will get B, and this B we will take 1 or 2. If we take 1, it is not going to work out. So, B, it has to cancel out with not B. So, we are taking 2 and not 1. 2 is not B or C. So, not B and B will go away. So, we will have C, and C we have the fourth one as not C. So, this actually would lead to a null clause. So, this is the method of resolution. So, in actual resolution what we would do is we will have a list of facts and a similar thing like the axioms that we did before, and then the proof, and the proof we are going to negate it, convert all these into CNF, and from CNF apply resolution like this until we get to a null clause. And if we are able to get a null clause, then we say that the proof exists. So, let us look at an example here. So, this is a practical example of diagnosing why a printer is not working. It is actually all these are going to show it is a contradiction, not prints or printer jam or low ink, not low ink or print. This actually is going to indicate low ink implies prints. Paper jam, not paper jam or print, this is actually going to indicate paper jam implies if there is paper jam it prints, if there is low ink it prints. So, it is kind of representation like this, and what we are going to do here is we are going to show the inconsistency, and in fact, some of our assumptions may be wrong while we are considering. So, let us start this. Again I will number here 1, 2, 3, 4 and fifth one, so that it would be easy for me to work on the resolution part. Suppose we take not prints, this is fifth one, printer is not printing. I can take the first one, low ink or prints. So, that we would get as not low ink, and this not low ink and 3 we would get a null clause. Suppose if I have taken the other way also, not paper jam with prints, the result we would get as paper jam, then also we would get a null clause. So, either way we would know that the some assumptions with which we have taken these are actually inconsistent, which is, and we have to correct that assumption. That is the part of resolution or the observation or the reasoning process that we are talking about. Now, the next one what we are going to see is we would first convert into predicate logic, and from the predicate logic we would convert into CNF, and from CNF we will go with the resolution. So, the set of facts look like this. First one is John likes all kinds of food, second apples are food, third carrots are food, fourth anything anyone eats as isn't killed by is food, 5 Bill eats peanuts and is still alive, 6 Sue eats everything Bill eats. From these we have to prove that John likes peanuts. For this set of facts, the first step would be we have to convert into predicate logic, and from the predicate logic we will convert into CNF and then resolution. Let us start with the first one. John likes all kinds of food. We can write it as for all x, if x is food, then John likes it, likes John comma x. This is the predicate logic expression for the first one. For the second one, apples are food, food of apples, and third one, carrots are food, food of carrots. Fourth, anything anyone eats and isn't killed by is food. This is third. Anything anyone eats. So, I am naming two variables x and y, one for person and food having the variable as y. So, anything anyone eats of x comma y and isn't killed by and not killed of x. Here x is a person. So, if you see the way that I have written eats of x y, first x eats y and not killed of x, x is a person, and that would go with the food also. Similarly, food of carrots, the food of x. So, you can see the predicate is being the same, and if it is not killed by is food, I am saying y is food. This is the representation for fourth one that I am varying. Again, the representation for each one of you may vary, but ultimately it should be consistent enough. Fifth one, Bill eats peanuts and still alive. So, I am going to have eats Bill peanuts and still alive. I am just writing it as not killed of Bill. Sixth, Sue eats everything Bill eats. So, whatever that I am going to name it as x eats whatever Bill eats, that Sue eats. And if you see this eats, f eats x y eats u x, the predicate will be the same, and the order in which the person and food also is there, the argument within this, that also remain the consistent with all the set of facts. Seventh, we have to prove John likes peanuts. So, it would be likes John peanuts. So, this is a set of predicate logic structure. Now, from this predicate logic structure, we have to convert into CNF. So, for the first one, it would be not food of x 1 or likes John x 1. So, if you see this 1 here, this represent the normal values that we said in the last class where we converted into CNF. It should be consistent with the other set of facts. The second one is food of apples, that remains the same, that when converting into CNF 2 and 3 will be the same, food of apples, and third one would be food of carrots, that would be the same. Fourth, eats of x y. So, that when we convert into CNF, that would be not eats of x y, and this would be a big bracket, and not killed of x or food of y. So, when this negation is pushed inside, so this becomes not eats x y or killed of x or food of y. Now, when we look at the standardization of it, this becomes not eats, because I have used x 1 already. Here I would be using x 2 y 1 or killed x 2 or food y 1. Then fifth would be 5. I can split it into two clauses, one is eats and another one is not killed. So, 5A would be eats Bill peanuts, and 5B would be not killed of Bill. Sixth, this clause would be not eats Bill. Since I have used x 3 here, I will take x 2 here, I will take x 3 for sixth one, or eats Sue x 3. Then seventh, when I am pushing into CNF or a set of clauses in resolution, I have to negate the proof, the last statement. So, it would be not likes John peanuts. So, from here, these are the set of CNF. From here, we will get into the resolution. So, if you check, we have standardized this as x 1, this to x 2 and y 1 for food, and x 3 here. So, now we will go into the resolution from the CNF. Now, if you see, the resolution would be, first you can just take a look at the previous slide. 7 with 1, we would be substituting peanuts with x 1. So, this will become not food of peanuts, and then this with 4, this would be peanuts, we will be substituting in the place for y 1, and this we would get as not eats x 2 peanuts or killed of x 2, and this is from the fifth clause, where we can substitute 5B, you can substitute Bill in the place of x 2. So, you would get not eats Bill peanuts, and when we have not eats Bill peanuts, we already have 5A there, which is Bill eats peanuts, and these two will lead to a null clause, and through this we can say that John likes peanuts. So, what we are concluding is John likes peanuts. So, what we have done so far is, given the set of facts, first we converted into predicate logic for all the 7 statements and negated this the proof has to be negated, which is returned on as 7, is not likes, and the set of predicate logic is converted into CNF, and from the CNF step by step we have done the resolution. And if you have noticed, I have started with the 7th, which is the proof, I have started the resolution here. Okay, but it need not be the case that we can even start among any of the CNF, but ultimately we have to reach the inconsistency state. So, from we are negating the proof, and through negation of the proof we are checking the inconsistency among the set of clauses, and through that we are proving the statement. So, that is actually the resolution with which we have done. So, coming to the summary of this session, what we have done is, this is an entire flow of the logic, the reasoning with logic side in unit 3. So, an example for forward chaining is given, and mostly here we have used only modus ponens, where we are going from the axioms to the goal. Also, in the backward chaining, it is a goal oriented proof, where we start from the goal and see whether the fact is remaining inside the knowledge base. And thirdly, we have seen the resolution process, where we are checking the inconsistency among the set of facts. and through these three methods the reasoning can be done. In the next session, we will be working on the knowledge representation techniques, where we will be using much of these logics. So, I will see you in the next session. Thank you.